Hello, I'm Dr. Prathanu Ghosh, and today I'm going to talk about internal loadings developed in structural members, especially in beams. So, what are our lesson objectives today? We need to draw the free body diagram with whatever external loadings acting on the beam and supports. Then we need to locate the internal forces. So, what are the internal forces? We are talking about axial force, shear force, and bending moment at the point of interest. And then finally, we need to compute values at the point of interest with direction and magnitudes. So let's see how we are going to compute internal forces. So here you see one of the example of a cantilever beam where one on the side of the beam is fixed, the other side is free, and we have two loadings acting on the beam. One is your concentrated load P1 acting straight downward, the other one is P2 acting inclined way, acting in the free end of the beam. And our aim to find out, let's say, at point B, which is our point of interest, to find out the internal forces. So to find out the internal forces at point B, what you need to do? We must pass an imaginary cut section AA, as you see in the picture, perpendicular to the axis of the beam through the point B, and then separate the beam in two segments. So when you separate the beam in two segments, we can imagine that the internal loadings acting on the beam will then be exposed and become external on the free body diagram of the each segment. So we see that when you cut it at point B, we are developing internal force NB, we are developing shear force VB, and we are developing bending moment MB. So either you can cut from the right or you can cut from the left, but overall it is maintaining equilibrium situation. So from one side, if it is moving forward, the axial force, the other side it will be back here. Whereas shear force from right side is downward, from left side is upward, and bending moment is counterclockwise from right side, and from left side it is clockwise. So as you see the sign convention, it is very much important. So either way you can cut it, either from left or right. You have to give your judgment. Wherever the sides has minimal loading, you need to go from that side so that your calculation will be a little bit easier. So let's talk about the sign convention. So how do you know axial force is positive or negative? How do you know shear force is positive or negative? How do you know our bending moment is positive or negative? So in 2-dimension, we use sign convention for axial force N, shear force V, and bending moment M. So normal force is said to be positive if it is creating tension or stretching, basically. If it is pushing or compressing, then it is negative. Then how do you know the shear force is positive? A positive shear force will cause the beam of the segment to act or rotate clockwise. As you see the picture here very carefully, both of these are creating clockwise here from right side as well as left side, the way it is rotating. So whenever it is rotating basically clockwise, the shear force, then the shear force will be positive. Similarly, we'll judge our bending moment sign convention. So let's see how we'll judge the bending moment will be positive or negative. So if the bending moment is trying to lift the beam concave upward, as you see the picture here, concave upward from both sides, left or right, then bending moment will be positive. So if it is concave downward, then it is negative. Similarly, shear force, if it is rotating counterclockwise, then it is negative. So another way of remembering it, if it is a smiley face, then it is positive. If it is a sad face, then it is negative. Another way to remember the sign convention of bending moment. So now we are going to solve one example problem to find out internal loadings at cross sections of the point C of the beam. So we are seeing a beam with one side pin supported internal roller, and then end of the beam is free, and we have all the way a triangular loading which is 800 pounds per feet is acting throughout the beam. So our aim will be to find out internal loading at point C, which is located 12 feet from point A. So how do you start? First step, to find out all reactions. What are the reactions? AX, AY, and BY. As B is roller, only the vertical support BY. A is spin, we are having horizontal reaction AX and vertical reaction AY. And then once you find out the reaction, we'll cut the section exactly at point C as we have seen, and we'll develop the internal forces and we'll apply the equilibrium equation from statics, which is summation of Fx is 0 to get our axial force, summation of Fy is 0 to get our shear force, and summation of moment is 0 to get our bending moment. All three internal forces will be computed, and then sign convention will be defined. So let's solve this problem. I'll close this one, and then we'll open Microsoft OneNote to solve the problem. So let's solve it. We have A pin, B roller, and then we are having D, which is the free end, and in between you have another point C. A to C is 12 feet and C to B is 6 feet. So B to D is 9 feet, and all the way we are having triangular distributed load, as you have seen the picture. So the load is acting downward. So that load, how much is the magnitude? Magnitude is 800 pounds per feet. So that means it is 0.8 kip per feet. So let's find out our reactions. So we have AY, we have BY, we have AX, and we have two equivalent concentrated load, as you can imagine. One triangular loading from this side, which is half 0.8 times 18, which is equal to 7.2 kips. The other triangular loading from this side, which is half 0.8 times 9, which is 3.6 kip. So distances are there. From here to here is your 12 feet and 6 feet already given, and from here to here is your 3 feet and 6 feet, measuring the triangle centroid. So let's find out our reaction. So summation of Fx 0 directly gives Ax is going to be 0. No other horizontal force is there. Then summation of moment, we are taking one of the support. Let's say we are taking the moment about B. It's going to be 0. So what are the forces? AY times 18. Then 7.2 times 6. Counterclockwise. AY times 18 is clockwise negative. And 3.6 times 3 clockwise. That gives your AY is 1.8 kips. Positive. Upward. Next step will be to find out BY. Summation of Fy is 0. AY plus BY minus your 7.2 minus 3.6 is going to be 0. So that gives your by is how much? 9 kips upward. So we got our all reactions. Now is our time to develop the internal forces. Which point? Our point of interest is point C. So we'll exactly cut through the point C and we'll develop our internal forces. So we need to find out our new height of the triangular loading exactly at point C. So let's find out and draw the free body diagram. So we are drawing a new free body diagram up to point C, A, C, which is up to 12 feet. A spin. We already know AX is 0. We know AY is 1.8 kip. And then our aim will be to find out the height of new triangle loading. We are cutting exactly at point C, as we can imagine. So our new height is by proportion 0.8 divided by 18 times 12 by proportion or similar triangle. So that gives 0.533 kip per feet. So our new equivalent triangular loading, area of the triangle, half 0.533 times 12, which is coming out 3.2 kip. And where it is acting, 2/3, so 8 feet. And then from there to the cut section is 4 feet. Our aim to find out all internal forces, so NC, VC downward from this side, and MC counterclockwise. So let's apply equilibrium equation. So we got our new height by proportion, we got our new equivalent triangular loading, and then we applied all the internal forces which you need to compute. So let's do that. Summation of Fx0, our first equilibrium equation. So that gives Ax plus NC is 0. Definitely Ax is already 0, so NC will be 0. Then summation of Fy. Who is there? Ay, and 3.2 is down, and Vc is down, which gives Vc is equal to Ay minus 3.2. So 1.8 minus 3.2 kips, negative 1.4 kips. So our original sign convention wise, it is downward from right side, but we got negative value. So that means it is going upward. So we see 1.4 kip upward. So we are swapping the sign. Then the last internal force, which is the moment at point C. So summation of moment at cut section is going to be 0. So who is creating the moment? Let's see very, very carefully. Ay times 12. This load times 4 and original MC. (3.2) times 4 and then MC. So that gives your MC is how much? If you do the math, it is coming out 8.8 kip feet. Positive value, and we got counterclockwise moment, so it will be counterclockwise. No change in sign. So that gives you your all internal forces at point C. That's what we try to calculate. So step by step, just recapitulation. First, find your reaction, then make a cut section at the point of interest, and then get your new loading with free body diagram, and then develop the internal forces, apply equilibrium equation, and get those forces with magnitude and direction. So right now you have learned this part. For your homework, determine the internal forces at point C of the beam, which is basically a simply supported beam with 4 kip per feet triangular loading from point A to point C. So that ends the lesson for internal forces. Hope you have enjoyed it.